Hey guys, welcome back to my channel Euclid Mathematics. In my today's video, we are going to learn one of the important tests from real analysis. And along with that, we go through some of the examples also. So here, Yeoman test. Yeoman test, which is the most important test in a real analysis for to check any type of a sequence of function, whether it is uniformly convergent or not. So it is the most important and necessary test, necessary and sufficient test to check whether sequence of a function is uniform convergent or not. There are multiple types of the test, but they are having there some limits. But when we apply Yeoman test to our sequence of a function, we get the easily and perfect uniform convergence. So let's start our today's lecture with the Yeoman test for sequence of function from real analysis, which is the most important topic for all type of competitive exam. So here, Yeoman test, it says that if sequence of function f and x be a sequence of function on I, okay, so on interval I it is defined that sequence of function, and fx be the limit of function. That means when we apply limit n tends to infinity to our sequence of function, we get the fx, okay, that is the fx is the limit of function. So if we apply limit n tends to infinity f and x, we get the fx, okay. So by the definition we can write directly here, okay, sequence of function, okay, so we write directly here Yeoman, which is equal to supremum of x belongs to I of nx minus fx, okay. We all know the definition for uniform convergence, okay. So that used here to find out the value for Yeoman, okay. So here Yeoman is the result here, and once we get the value for Yeoman, which is in the term of n only, okay, which is in the form of n only, and when we apply limit n tends to infinity to that Yeoman, we get the some sort of answer. So if it is a 0, then that means our sequence of function, it is a uniform convergent, okay. And if it is non-zero, then we say that our sequence of a function, it is not uniform convergent, okay. So we know that we can apply pointwise convergent to check first of all whether our sequence of function is uniformly convergent or not, okay. So we can apply that point of convergent, okay. But here in Yeoman test, we do not have to worry about point of convergence. We can directly apply Yeoman test to the sequence of function, and we directly say that our sequence of function, whether it is a uniformly convergent or not, okay. So here it is important note here, this test is a very strong, because of that it's a necessary and sufficient condition, okay. And one more condition here, if limit n tends to infinity Yeoman non-zero, then sequence of function f and x is not uniformly convergent, okay. So it is non-zero, then not uniformly convergent, and if it is 0, then sequence of a function f and x which is always uniformly convergent, okay. So for better understanding that result, we go through some of the example. So let's start the example. So here we have example which asked in CSIR NET June 2017, which is for the 3 marks question. It is single answer correct question, okay. So to understand Yeoman test better, we have to follow some previous year questions, okay. So the concept will get more clear and transparent, okay. Now here let's read our question. So our question, it is here, for n greater equal 1, sequence of function is given f and x which is equal to x multiplied by e raised to minus nx square, and x belongs to real number, okay. And then we have to check the sequence of a function fn is whether the one of option is true, okay. So first option, uniformly convergent on R, that means sequence of function fn which is uniformly convergent on R. That means for every value from real number, our sequence of function is uniformly convergent, okay. Now in second option, uniformly convergent only on the compact subset of R, okay. What is option B? Uniformly convergent only on compact subset of R. That means only there exist compact subsets, okay, where our sequence of function is uniformly convergent. Now third option, bounded and not uniformly convergent on R. That means it says that option 3, that sequence of function, it is not uniformly convergent, but it is bounded. And now option number D, it says that a sequence of a function is unbounded function, okay. So we have to check here whether it is bounded or unbounded, okay. Now let's go for the Yeoman test. We solve our example by using Yeoman test, okay. So here Yeoman test, it says that by Yeoman test, we know that the first condition, limit n tends to infinity, if we apply to f and x, we get the fx, okay. And the second condition for Yeoman test, it says that for finding the value for Yeoman, we have to apply supremum for our given fx, okay, given f and x, okay. So here the sequence of function, it is the definition from uniformly convergence of a sequence, okay. So here for finding Yeoman, we have to find out the value for f and x and fx. So already f and x which is given in our example, okay, sequence of function is already given, and fx, how we obtained fx? To apply limit n tends to f and x, then we get the fx, okay. So now let's find out the value for f and x and fx and substitute here in Yeoman, okay. And we know that if the sequence of function which is uniformly convergent on interval I, if and only if the limit n tends to infinity, Yeoman is going to be a 0, okay. So now here we can see fnx which is equal to xn e raised to minus nx square. Okay, so now first of all find out the fx. That means we need to apply limit n tends to infinity to fnx. Okay, so here in my first option, limit n tends to infinity fnx, that means limit n tends to infinity x upon e raised to nx square. Okay, that means the power is negative. Okay, and when we transfer it to the denominator, it gets positive. Okay, and when we apply limit n tends to infinity to the denominator, that denominator goes to infinity. Okay, so here denominator is infinity, and any number divisible by infinity, it always 0. Okay, that means we got the value for limit n tends to infinity fnx which is equal to fx which is a 0. Okay, that means I got the value for fx is a 0, and I know here the value for fnx. Okay, so now substitute both of these value and let's go for the further calculations. So here in my second option, I added here mn as a value for fnx and fx. Okay, so fnx which is given in our option, and we have to check whether the value from real number, our mn, gives finite value or not. Okay, so fnx it is here and fx it goes to 0. Okay, now the remaining term here, only the modulus of supremum of x belongs to R. Why this supremum is given? You all need to know when supremum it comes, it is for only multiple type of the function. If that mn include more than 2 functions, that means we have to choose only the supremum value between that. Okay, so that's why supremum is there, but in our case we have only one fnx. Okay, so we don't have to worry about that supremum. Okay, so here fnx it's left here only, but here in our mn we cannot decide whether that mn 0 or not. Okay, so we have to check that out whether it is 0, non-zero, or having any constant values. Okay, now consider that mn x e raised to minus nx square by some other variable. Okay, so I consider that one as y which is equal to x e raised to minus nx square. Okay, so we have to differentiate to figure it out whether the value for it is a constant or any type of the number which is in the form of n. Okay, which we required further. So y which is equal to here, I consider here, and now differentiate it. Okay, I hope so you all know the differentiation. Okay, so this is a function of u into v. Okay, apply by part rule from the differentiation, then next y dash it will come. Now here y dash differentiation, first variable, second as it is differentiation of first x is 1 plus e raised to minus nx square, differentiation of e raised to x, it remain e raised to x, and differentiation of minus nx square, it will be minus n. Okay, and it to here x it remains same, and that x will be here. Okay, so it is the easiest differentiation. I hope so you all are aware about that differentiation. Okay, so y dash it is here, so arrange these terms. So I got the y dash here, and after getting y dash, we cannot say that the value constant or variable, because it contains most of the variable and constant combination. Okay, so we try to find out the value as we use this method in our solution of equation. Okay, so that time we consider that equation as a 0 and try to find out the value for that particular variable. Okay, so similar I applied here, just a basic knowledge applied here. This y dash is a 0, I substitute it here because I want the value for n, that's why. Okay, n or x, so that's why I substitute y dash 0, so it is here. Take e raised to minus nx square common from here, we get the next term e raised to minus nx square 1 minus 2 nx square. Okay, so next term here 1 minus 2 nx square which is equal to 0, or e raised to minus nx square which is equal to 0. That means their multiplication 0 means this one is 0 or this one is 0. Okay, so if e raised to minus nx square 0, is it possible e raised to minus nx square 0? Never, it is never possible. We know that exponential term never be a 0. Okay, okay, so it is always bigger or smaller than 0. Okay, so it is never 0, so it remain only 1 minus 2 nx square is 0. Okay, so it is left over here 2 nx square which is equal to 1. Okay, so 1 I took it here for the other side, so 2 nx square which is equal to 1. So now find out the value for x square. So 2n it is to the other side, x square which is 1 by 2n. Okay, so I want the value for x, so x it comes, remove that square root, so 1 upon 2 times root n. Okay, so go for the next step. So here I got the value for x is 1 by root 2n. Okay, and we have to substitute that value into mn, so we get the value for mn then. Okay, so we know that the mn is the x into 1 upon e raised to minus nx square. Okay, plus nx square. Okay, when it comes to the denominator it get plus. So x it is here 1 by root 2n, 1 upon e raised to n, x square it remain 1 by 2n. Okay, so x is 1 by root 2n means x square 1 by 2n. Okay, so mn I got the value for mn 1 upon 2 root n, so n get cancelled. Okay, so e raised to power 1 by 2, so e raised to power 1 by 2 means square root of e. Okay, so now our mn test, it says that when we get the value for mn, we have to apply limit n tends to infinity on it. Okay, so when we apply limit n tends to infinity to our mn, and mn has a denominator n. Okay, because denominator n is present here, and when n goes to infinity, denominator goes to infinity, and when denominator goes to infinity, our mn goes to 0. And our mn test, it says that if limit n tends to infinity, mn it goes to 0. That means if limit n tends to it is having value 0, then our sequence of a function fnx is uniformly convergent on I. Okay, so we can apply pointwise convergent also But I feel that to applying directly MN test, it is quite easy and time saving strategy. Okay, so if you solve more example, this one will come more easier for you all. Okay, I hope so you all have understood my today's lecture on MN test and one example from CSIR NET. Okay, so I will post more videos on some examples from CSIR NET or other competitive exam or exams on our MN test. Okay, I hope so you all have understood my today's lecture. Thank you everyone. Thank you for my lecture.